The directional gyro indicator, which is often called the direction indicator or DI, provides a stable directional reference in azimuth for maintaining accurate headings and for executing precise turns. There is no magnetic element in the direction indicator, so it's not north-seeking, and it must initially be synchronized with the magnetic compass. The synchronization must be checked at regular intervals because of real and apparent gyro wander, sometimes called gyro drift. The directional gyro indicator doesn't therefore replace the compass. Its stable, deadbeat indications are complementary to the north-seeking capability of the compass. Having no magnetic element, the directional gyro indicator doesn't suffer from the compass turning and acceleration errors produced by the vertical component of the Earth's magnetic field. The directional gyro indicator employs a tied gyro. That's to say, a gyro having freedom of movement in 3 planes mutually at right angles to each other, but with the rotor axis maintained in the yawing plane of the aircraft. This means that the rotor axis is horizontal in level flight, and because of gyroscopic rigidity, it provides the datum from which heading can be measured. The rotor is mounted in the inner gimbal, on bearings mounted in the outer gimbal, which has restricted freedom to turn. The outer gimbal can rotate through 360 degrees about the aircraft's vertical axis, on bearings within the case of the instrument. Note that the rotor axis, the inner gimbal axis, and the outer gimbal axis are mutually at right angles. During a turn, the aircraft and the instrument case turn on the vertical axis bearings of the outer gimbal, while the gyro rotor, gimbals and cylindrical indicating scale all remain fixed in azimuth because of gyroscopic rigidity. Heading is indicated on the cylindrical indicating scale by a lubber line painted on a glass window in the instrument case. Another type, shown here, has a circular vertical card indicating scale geared to the outer gimbal instead of the cylindrical scale. With earlier designs of directional gyro indicator, the rotor is driven by twin jets of air applied from the outer gimbal ring as shown in here. Suction is applied to the case of the instrument, and replacement air enters the case through a filter and is ducted to the jets on the outer gimbal, which act on buckets cut in the rotor. The jets not only spin the rotor, but also serve to maintain or tie the rotor axis in the yawing plane of the aircraft. If the axis of a gyro rotor departs from its chosen direction, it's said to wander. If the axis of the gyro rotor wanders in the horizontal plane, as indicated by the horizontal arrow in this diagram, it's said to drift. A weight hung on the gimbal at point A will produce drift. If, on the other hand, the rotor axis wanders in the vertical plane, as shown by this arrow, it's said to topple. Manufacturing imperfections on the gyroscope cause small rates of random precession. Other terms given to this precession are balance wander or, if the precession is in the horizontal plane, mechanical drift. The imperfections concerned are uneven rotor bearing friction, unbalanced gimbals, and friction in the gimbal bearings. In-flight turbulence may increase the effect of these imperfections. The precession caused by application of an external force to a gyro is another example of real wonder. Consider a space or free gyro, as shown here, with the rotor axis horizontal and aligned with the geographic meridian. The rotor axis is indicating the direction of true north on the Earth, and is also aligned with a point at an infinite distance in space. Sometime later, when the Earth has rotated in space, the gyro rotor axis is still aligned with the same fixed points in space, assuming no other disturbing forces, but no longer indicates the direction of north on the Earth. It's therefore changed its alignment, according to the earthbound observer, by 70 degrees in this case at this latitude. This is apparent wonder, or apparent drift, due only to the rotation of the Earth about its axis. For thousands of years the oxide of iron called magnetite has been observed to attract small pieces of iron. This property is known as magnetism. Another property for which magnetite was known was its north-seeking capability. If it was mounted on a piece of wood to allow it to float on water, it would swing around and align itself in a roughly north-south direction, so acting as a primitive compass. In more recent history, it was found that some metallic elements and alloys, mainly ferrous, iron and steel, could be given these properties, bars of such magnetized material being known as magnets. The field of a magnet is the space around it in which its magnetic influence is felt. This may be illustrated by placing a piece of card over a bar magnet and scattering iron filings on it. When the card is shaken or tapped, the filings will take up the field pattern as shown in this diagram. This same diagram illustrates that the lines of force traced by the iron filings converge towards small areas near the ends of the magnet. These two areas are called the poles of the magnet, and this is where the properties of magnetism are most strongly displayed. Magnets can be made in various shapes, but each magnet always has two poles. A unit pole cannot exist. If a magnet is cut into two pieces, each piece will have two poles. A freely suspended bar magnet, or a compass needle, in the Earth's magnetic field will align itself roughly north-south. The end which points north is known as a north-seeking or red pole. The other end is a south-seeking or blue pole. The Earth behaves as though a huge permanent magnet was situated near its center, producing a magnetic field over the surface of the Earth. You may remember, we said that a freely suspended magnet in the Earth's magnetic field would align itself roughly north-south. For it to do this, its north and south-seeking ends would have to be attracted to poles of opposite polarity. Thus we portray this huge hypothetical permanent magnet inside the Earth with its blue pole under the Earth's magnetic north pole and its red pole under the Earth's magnetic south pole. This diagram shows that the poles of this hypothetical Earth magnet do not lie on the Earth's spin axis, this lack of symmetry giving rise to magnetic variation. The Earth's magnetic north pole, the blue pole, lies at present beneath northern Canada, in the area around 70 degrees north, 95 degrees west. The magnetic south pole, the red pole, being below Antarctica at about 72 degrees south.